A very good morning to all the respected chair members, professors, and my fellow authors. Today, as Sarthak Malik, a BTech student from IIT Roorkee, is going to give a brief talk about a work on interpretable AI. The topic of our paper is towards interpretable facial emotion recognition. Before starting, I would like to give an outline of what this talk will be all about. Firstly, I would be introducing about the topics that we have addressed in our paper, then our contribution made towards this direction, and the literature survey, that is, all the works that have already been done. Then we will dive deep into the problem formulation, the architecture, and the new DNC shape algorithm that we have proposed. At last, I will be showing few results related to the confusion matrix and the feature maps that are outputted by the DNC shape algorithm, and then we will analyze them. Beginning with the introduction, as we have seen with time, the deep learning models have shown a great potential, and their accuracy is increasing day by day, made the field of medical field, emotion analysis, or speech analysis. They are performing better and better in each field. But what is stopping them is their black box nature. Interpreting a DNN model is a tough task. We can't tell what are the features that the deep learning model is concentrating or how it's concentrating, why he have given the importance to that particular feature. It may be possible that there is high accuracy because of some noise or the model seeing features that are not even relevant. So this led to development of a new field in AI, the interpretable AI. This contains few algorithms like SHAP, LIME, and GradCam. Many of these are computationally very expensive, while others don't have any mathematical proof, while some, like GradCam, are good and even faster. The problem with them is they are prone to shift in the image. Like a little shift in a GradCam can lead to a huge change in the feature map. Again, this caused them stress. So this motivated us to explore the field of interpretable AI, and we developed a new method, divide and conquer based Shapley additive explanation (DNC SHAP), and applied the same on the FER system that we have proposed. Speaking of our contribution, we have proposed a deep learning based facial emotion recognition system that can classify the features in 7 discrete classes. Then we applied our novel DNC shape algorithm on this system to analyze the feature maps we get and the highly relevant features or pixels we get from this. At last, the main contribution of this paper is the DNC shape algorithm. We have incorporated the divide and conquer algorithm with the Shapley values to get the highly relevant pixels or features in linear time, which requires a quadratic time earlier. Now, let's do a brief literature survey. The field of emotion AI is well known and booming in research. There are various research papers done in this field, as we can see here. These models can be classified basically in two ways. First is the traditional based ML models. These require techniques of handcrafted feature extraction. The techniques like oriented gradients, local binary pattern, and Gabor wavelets are used. While the other are the end-to-end based deep learning models. These models don't require any handcrafted features and can work their own. Also, people have added some attention layers in these models. All these models work on 7 basic features of happy, sad, fear, disgust, surprise, anger, neutral. These are the pioneering work of Paul Ekman. We have used the same features in this model. Speaking of interpretable AI has gained importance the last few years. It is because of the black box nature of DNN and the mistrust that it creates. Interpretable AI is basically of 3 types. We can speak of attribution method, perturbation based method, or backpropagation based method. Attribution based method means assigning some relevance or importance code to each feature, in this case of images, each pixel, to get a feature map. The main work in this field is the SHAP by Lundberg and its team. It is based on Shapley value and it's a quadratic in computation. Next is the perturbation based method. In this method, we change each feature by slide and see what is the impact on the prediction. This helps us in giving importance to each and every feature. The main work in this field is LIME. LIME is not mathematically proved yet, and so we can't trust this completely. It collides, it is same as SHAP in case of linear model, but in non-linear model, it disagrees with SHAP. Last is the backpropagation based method. In this method, we backpropagate the net from the top to bottom to get the relevance score of each and every pixels. This includes saliency map and GradCam. This category is great, but they are very prone to slight change in the image. Now, let's see what we want to achieve in this paper mathematically. Let us consider a neural net F that maps n dimensional feature x to label m, y1, y2, y3, and ym, and the features are x1, x2, x3, and xn. The goal of this proposed approach is to find the Shapley values or the importance of each pixel xi in getting the label yj. Looking at the methodology of our FER model, we can see in figure 1 that our model is built on top of VG16. We have added 4 residual layers to it and concatenated them at the end. The idea to this came from the fact that each block in VG16 give us some features. It may be possible that these features dilute as we propagate through the net. So we thought of adding these features at the end, and this worked out to be great. Next comes our DNC-Shape algorithm. As I have already discussed, DNC-Shape here means divide and conquer based Shapley additive acceleration. Here we have incorporated divide and conquer with Shape algorithm to reduce its time complexity. Shapley values basically are from game theory and are permutation combination based. They are NP hard and require exponential time. But this is not possible in computation. So what we did was we incorporated divide and conquer. That is, we divided the whole image in the half and we calculated the importance of each half. Again, we divided these halves into halves and calculated their importance. Combining them, we get a feature map here. The red part here shows the high relevance area while the blue shows the low relevance area. And now let us discuss the ablation study which has led to the architecture that we have proposed. Firstly, we just used a pre-trained VG16 SNet. We were not able to get a great result. Then we built a baseline model based on our idea of residual layer. We just included 2 residual layers and a dense layer of size 4096. What we observed was that the output accuracy was fluctuating too much while training. So we concluded that the neurons are too many in the dense layer and we reduced the size of dense layer 2048. Also, we incorporated 4 residual layers as we have seen in the final net. This give us the accuracy. This give us state-of-the-art result in 3 of the 4 datasets that we will discussing later. The experimental setup used for this is NVIDIA Tesla T4 GPU with 2560 CUDA cores and 2320 Tensor cores with 16 GB of virtual RAM. The dataset used by us are FER13, FERG, GEFI, and CK+. All the experimentations are performed using 5-fold cross-validation, IDEM optimization, categorical cross-entropy loss, and batch size of 32 for FER13 and 16 for rest of the dataset. The model is trained up to 100 epoch for each of the dataset with a learning rate of 8 into 10 to the minus 4. Now, let us summarize the results that we got in this paper. Firstly, our FER system, the facial emotion recognition system, is able to get state-of-the-art result in 3 out of the 4 datasets we have used. The results here are 62.62%, 99.68%, 99.97%, and 99.67% for the 4 datasets. This can be seen in the confirm matrix here. I can also see the table 2 result comparison that FERG, JFE, and CK Plus got the state-of-the-art result. Next comes the feature maps given over by the DNC-Shape algorithm for various classes of anger, disgust, fear, happy, and sad, surprise, neutral. Here we can see the feature maps. The anger part, the face of the nose and the lips of the woman are most highlighted. For the disgust, the eyes and the nose that is formed in this way that show disgust is highlighted. For the fear part, we can see the facial is distorted and also the chin is lower. So the algorithm is focusing that area. Happy, it's clear that smile will be seen and the teeth. Surprise, it's clearly visible that the open mouth can be seen. So this is how we have outputted the feature map using DNC-Shape algorithm. Table 3, we can see here the table 3 compare the theoretical cost, the execution time of various interpretable algorithm. DNC-Shape is just after GradCam, but I've already discussed the problem with GradCam. They are not trustable. They changes the feature map a lot. Even if we change, even if we propagate an image a little bit in x-axis or the y-axis direction, so they are not trustable. Also can't be proved. While DNC-Shape algorithm is mathematically proved, algorithm from Shapley values is faster than both Shape and line. Table 4 here shows the feature overlap that I was talking about. The DNC-Shape algorithm overlaps the most with the Shape algorithm that is currently used in the industry and is a quadratic, while our DNC-Shape is a linear algorithm. Now, I would like to conclude our paper with these points. This paper proposes an interpretable deep learning based FER system, which we can analyze our result. We have analyzed the result of FER model using our newly proposed DNC shape algorithm. Our DNC shape algorithm gives the highly relevant feature for each class, and it is consistent for all the images in a class. Also, the features that come out for different data set is consistent for each class. With this, I would like to conclude my talk, and thank you very much.